I'm really, really pleased to introduce somebody who's been a friend for about 30 years. He was my student. I'm very proud of that. And he has become an advisor. Reid Hoffman is the co-founder of LinkedIn, a partner at Greylock Partners, and on the board of companies such as Airbnb and Microsoft. He's also on the boards of nonprofits, including Kiva and the Chan Zuckerberg Initiative. He's the author of several New York Times best-selling books on entrepreneurship and talent management. And of course, he's a graduate of the Stanford Symbolic Systems program. We taught him everything he knows. So, Reid?
This is the kind of leaders in doing various forms of technical and deep work panel. So that's what we're mostly focused on. You can think about it as kind of a compare and contrast in human intelligence and artificial intelligence and what we learn. And I can literally not think of a better panel. At least this is the perfect 4 panelists for this panel, in part because of the Human Artificial Intelligence Center high theme, which is catalyzing not just academia, but also industry and in public policy, and how do you bring that all together? And so we have in addition to a phone, we have both amazing experts here from academia and from industry. And of course, people normally in my role kind of say, oh, they need no introduction, and now I go on at super long length on introduction. So I'm going to spare my panelists that. I'm going to do a 1-sentence intro per person just to do this, although I may be able to make them blush in an appropriate 1 sentence. So I'm just going to simply go from closest to me further on. Jeff Dean, who many of my friends at Google have described to me as the world's best systems engineer, and also in charge of many different things at Google, including Google Brain. Professor Alison Gopnik from Berkeley, who was the earliest kind of person to note things like the relationship between mathematical models and children development, and kind of how to actually think about this in these kinds of systemic ways, and has been doing an impressive amount. Like literally, like I read a bunch of her stuff. This is the first time we met. I was super honored. Professor Christopher Manning, who anyone who's done AI has read his books in NLP. He's the director at SAIL here. And then Demis Hassabis, who is a childhood chess prodigy, but also the CEO and co-founder of the, also at Google, the amazing moonshot from DeepMind for artificial general intelligence. And when we were corresponding by email about how to kind of open up this panel, one of the things that I had proposed as a way to kind of start was to kind of say, well, this Turing test thing, which I presume everyone in the audience is familiar with, the parsing through language, which Alan Turing did in the very earliest days, what have we come to learn about it, and should we revise it? And Alison pointed out, saying, well, actually, in fact, he very quickly went on to say, maybe we should actually look at this as replicating what a child can do, because of that kind of cognitive development, and what are the kinds of things that come out of this amazing kind of cognitive richness and capability. So that's where we're going to start. And since it was your idea to actually go to the second refined version of the Turing test, I will start with you.
Great, thank you. Yeah, Turing, as usual, got it right in that second part of that famous paper. And what he was pointing out is a bunch of things that children, the best learners we know of in the universe, can do that current AI is still just struggling to do. So current AI, and we had a wonderful introduction to that in the lightning talks. Current AI is great at taking great big amounts of data and then being able to make predictions and discriminations based on those big data sets. It's not very good at generalizing to very different kinds of contexts. And children can take very small amounts of data and are extremely good at generalizing, making up new ideas. In particular, they build up structured models of the world. A second thing that kids can do that AI can't so far is that AIs are typically kind of locked inside of their own heads. Whereas one of the things that children can do is actually go out into the world and get the data, get the new information that they need. So they don't just rely on a programmer to give them the data. They do something that's a lot like scientific experimentation, except when 2-year-olds do it, we call it getting into everything. But one of the things that we found in our lab is that when they're getting into everything, what they're really doing is systematically getting just the information that they need to build those models. And at Berkeley, the other place, we've been doing work designing curiosity-based AI that would be able to go out, just get information and knowledge and explore the world for its own sake, the way 2-year-olds do. And the last thing, which is something that Mike mentioned, is that they're social learners. So again, children aren't just learning in isolation. They can take advantage of the centuries and millennia of culture of the people in their past. And as we've seen, even the youngest babies are incredibly sensitive and subtle about picking up information from the other people around them, including language. So there's three things: model building, exploration, social learning are the clues to how children can learn so much. And those are things that are still just at the beginning in terms of what AI can do.
And so as a panel, I'm trying to get some dialogue. Since Demis has also referred to Alison's work to me before, I'm going to ask you to go next on the industry side, also thinking about like what do we learn from children and how would you compare current state of AI with the current set of modeling a child's learning, causality, et cetera, and then where we're going.
Yeah, so I mean, when we started DeepMind back in 2010, actually at the heart of our approach was this idea of generality being the key to intelligence. So actually Shane Legg, my co-founder, he did his PhD on the mathematical foundations of intelligence. And as part of it, he looked at all the definitions in history of the last couple hundred years about what intelligence is. There's still not an agreed definition. But the one common strand he found was that it was the idea of performing well across a wide range of tasks. So, and we adopted that as our kind of working definition for AI as what was the key to flexible general intelligence. And it's this, this very quick ability to use your knowledge from one domain to another domain. So it's sometimes called transfer learning. And it's something, as Alison points out, that we still don't know how to do yet in AI. There are many theories about what's needed, including like what we think that you're going to need abstract concepts or some ability to form abstractions, which from not just sort of have implicit knowledge about what you're doing, but actually explicit knowledge about the tasks that you've mastered. And I think that child development is actually a really interesting place to look. Because if we're building learning systems, one of the key things that we found out over the last 5-10 years is that you need to design curricula. So you actually need to design a kind of teaching program and a set of experiences so that build up in difficulty so that the system can start off knowing nothing, but slowly and incrementally build up to mastering a difficult task. And you can't just go from 0 to 1. You actually need to do easier versions of that task and then build up in the way that we teach children. So I think child psychology is really interesting to look at, child development. I also think there's a lot of value in looking at animal evolutionary history and animal psychology, and we do that at DeepMind as well as cognitive neuroscience. So, and we've always had that at the beginning. I mean, my training has been as an undergrad as computer scientist, and then my PhD was in neuroscience. So we've always believed in bringing together learnings from neuroscience and psychology with machine learning, and I think that's the way forward for AI.
Chris, one of your colleagues here at Stanford was contrasting the kind of the word count between the OpenAI model, right, and actually how quickly children learn. In what you're seeing in terms of NLP and the return to kind of this natural language processing, how does this mode of where do we stand currently regarding children, and what could we be learning from what the children do that kind of show us some interesting path forward?
Great. Yeah, so I'd like to pick up on some of what Mike, Frank, and Alison Gopnik just mentioned on social learning. My background is in working with languages and linguistics, and while there are many aspects of social learning, a huge, huge part of that is the use of language. So, The exact details are somewhat in dispute, but it's quite possible that the basic intelligence of a human being isn't very different than a chimpanzee or a bonobo, that other kinds of primates can do sort of most of the things that we think about human beings as good at. They not only have, great vision systems, great haptic systems, but it's been shown that they can plan, etc. But human beings have managed to get so much further than chimpanzees over the last few thousand years, and essentially the difference is that we have this power of language, which is something that, so we don't just have individual brains inside creatures, but human language essentially gave us the power of networking, right? That we can network together human brains through the use of language. And that's then also an enormous part of then how children are able to learn so much so quickly. And yeah, so there's this sort of enormous gap between our current AI and human learning, where current AI can work well if we have millions or billions of examples. We can essentially externalize all knowledge, and then the systems can learn pretty well, but that's orders of magnitude apart from how human learning happens. And as Percy Liang also talked about in his keynote talk, that you can get this orders of magnitude more efficient learning if you can use tools like human language to explain patterns, rules, generalities, things to pay attention to. And it's those kind of interactions that parents and other caregivers regularly have with little children.
So speaking about efficiency, obviously one of the things that current ML does very well is learning certain tasks almost at amazing speed and superhuman capabilities, but we're still working on the generalities.
Yeah.
Jeff?
Yeah, I mean, I think where we are today is you can actually solve lots of different kinds of really interesting problems by collecting large data sets in vision and in language and in speech recognition. And train a system that can do that one thing, maybe a very difficult thing, but it does only that thing. And occasionally you might do learning of a few different tasks together. But I think what we really need to get to from where we are today is how do we actually train systems that can do thousands of things, tens of thousands of things, and then can leverage their expertise in capabilities of doing those things to bring to bear on a new thing that they're confronted with, in a way that is reminiscent of how children in early childhood learn to figure out, how to do a new thing. It's like, it's kind of like these other 7 things I know how to do. There's this one little bit I don't know how to do. Let me experiment with that for a bit and figure out how to solve that new thing. And can take cues in terms of language or other things. I really think that's the direction we need to be going as a field, is how do we actually build much more general systems that can essentially take not a new training example and do well on that, but a new task and do well on that.
So Jeff and Demis, how much is the kind of the academic study of kind of the cognitive development of children part of the current research program? Right? Like, how much does that factor into, here's what our next things are, and here's the next things that we need to be doing, and what are the things that you most kind of look at interacting with academia about to facilitate that?
Well, it's an area we follow very closely, and we read all of Alison's work and people like Liz Spelke, and there's a whole bunch of really great researchers in this area. So we keep up to speed with that literature. I mean, I think one of the key issues actually is that children, obviously, they develop, they can learn incredibly quickly, as everyone's pointed out on the panel, but they come with a lot of prior knowledge in the sense of what they're born with, what our genes are born with, and what we're encoded with throughout our kind of evolutionary history. So children start with that, and their brain structures are sort of suited to the kind of world they're going to find themselves in. Of course, they're extremely adaptable, so we can learn how to use iPads and iPhones that didn't exist when we were hunter-gatherers, but the fundamentals of learning are sort of already there, and the structure and this desire to use language and so on. So there's a lot of that is probably already intrinsic in the evolution of our brains. So one interesting question is that there are probably multiple ways of building artificial intelligence, but one interesting question is the size of that search space relative to the number of solutions in it, and the human brain is the only existence proof of a solution that we have. So I've always thought it was, given, my betting is that the search space is far larger than the number of, the small number of solutions. So it's worth us studying and trying to reverse engineer the one that we know about, which is the human brain. But the interesting question is with all these prior assumptions and priors that children have, and that's what allows them to learn really quickly, which ones of those are really needed in a general case. So I sometimes talk about what we're trying to find in computer science, at least in artificial intelligence, is the minimum set of maximally general priors. That's sort of what we want. And children are a good place to start. They're probably not the minimal set because we're biological creatures and we have all these extra add-ons that we need because we have to exist in the world. But they're a good clue. Like maybe you can start there and pare down and then get to the true sort of mathematical minimal set that you require for generalization. And what I just following from what Chris was saying, of course, language is where we want to get eventually. One of the big things I see challenges in AI today is bridging the gap from messy sort of perceptual data that we now know how to deal with reasonably well, like vision with deep learning and reinforcement learning, these kinds of techniques. But we need to bridge back to the kind of classical AI, if you like, of symbolic reasoning, which in the past was using logic systems and so on, handcrafted logic systems. But we need to build back to there using our learned systems. And there's sort of this chasm in between where I suspect things like abstract concepts lives, and that we need to bridge until we can get to language. I mean, all of us agree we need, systems could use language. It would be so much better. They'd be able to learn faster. They'd be able to explain themselves and so on. But one of the issues is how do we ground that language in real concepts and real knowledge about the world?
Yeah, I agree with what Demis said, and I think it's really important. We don't know how to build intelligence in a artificial way, and so it's important to draw inspiration from all the other fields of study that are looking at human intelligence, other kinds of intelligence, to get lessons about how we might want to sort of explore this new field. And I think that means understanding things from neuroscience as we learn more about sort of various kinds of brain structures, understanding more from child psychology about how humans acquire skills in an early environment. And I think also that can draw inspiration from how real neural structures are very energy efficient. I think that's going to be an important aspect of how do we actually build large-scale computer systems that are very intelligent but energy efficient, is what inspiration can we draw there. Now, it's important not to take this too far because silicon and wet biology have different strengths and weaknesses, but I do think looking across lots of different disciplines at the kinds of lessons you can draw from what we are now understanding about other organisms is going to be helpful.
So Chris and Alison, how would you elaborate on this current research program from the industry side? And in particular, what would you think is kind of the do's and don'ts as from thinking about it from the kind of like the childhood development or the kind of the human perspective, and maybe perhaps with particular focus on language, which is probably the next thing we're going to get to.
So I think one of the things that we've learned is that it isn't just about representation. It's also about things like motivation and affect. So in kind of classical reinforcement learning, in a sense, you could think about that as a way of formalizing motivation. But one of the things that's interesting is that we have these kind of intrinsic cognitive motivations that we see even in very young children. And that's a really characteristic piece of what children are like that we don't understand very well. We don't quite know how that works. And that would be a really interesting thing to try to build into the kind of RL context. But I think another thing that's interesting is that the kind of traditional tension has been between the kind of handcrafted, logical AI where we build a lot of the structure into the system, and then on the other hand, these systems that are very good at learning from data but aren't very structured. And the really striking thing that we see with children from the get-go is that they have this capacity to infer abstract structure from data. So it's certainly true that they start out with a lot of abstract structure, and that makes it easier, but they can get to really new kinds of abstract structure from data. So rather than building it in the kind of classic way or just learning, there's exactly, I think Demis is exactly right, that there's this capacity to use things like transfer, generalization, or analogy, or causal inference to build structure from data. And I think that's really going to be the thing that's going to be the key.
Yeah, so I really agreed with what Demis was saying about how can we sort of get back beyond doing the kind of large-scale machine learning, which has been great for perception tasks, but also you can think of most of machine learning classification that way, right? That you have all of your inputs to it, and you're just training as a one-step classification, this function that takes you from the inputs to, okay, you know, this is or isn't a spam piece of email. But precisely what little kids do is that they can explore and experiment, see what the parts of something look like, and figure out what this part means, and then try and see what another part means, and then they can compose knowledge together. So it's getting back to having computers that are capable of reasoning and thinking, and an essential part of this is that we have to have this compositional knowledge where you can sort of take parts you understand, figure out other parts, and put them together to make something bigger. And that way you're then combining knowledge and reasoning. Knowledge and reasoning used to be the central hub of artificial intelligence work in the 1980s, and the truth is it's kind of been lost in the 2000s and 2010. And yes, going forward into the 2020s, we absolutely want to be exploiting all of our new understandings of how we can learn from data, because clearly little kids learn almost everything that they know. But we also then want to be getting back into having the use of knowledge and reasoning, the kind of human thinking that Daniel Kahneman refers to as thinking slow. That's the kind of thinking that we haven't really worked out how to get artificial intelligence to do.
So before we get to kind of like what do we expect of the language and kind of wrapping back into the almost the first version of the Turing test, I want to pick up on one of the things that Alison said, which is the interplay between what you would think of as the classically cognitive capabilities, because Chris is also doing this knowledge representation, you know, planning, reasoning, but also the kind of social motivations, right? The kind of the infrastructure, like the fact that we interact socially, the fact that we have a set of drives that almost kind of drives this quote unquote unsupervised learning as a way of doing this. How does that factor into how you're thinking, Demis and Jeff, in terms of what the next few years look like?
Yeah, I mean, I think Alison's absolutely right. We're intrinsic motivation, as it's sometimes called, is a huge sort of research area now. You know, what sorts of, in reinforcement learning, you get rewards from the environment. So let's say you're playing a game, you get a score, or you get a reward for winning the game. But a lot of the things you do in the real world, you don't get clear reward signals from in that sense, certainly not short-term ones, you know, maybe over a very long time arc. So you get these kind of quite difficult mathematical challenges like credit assignment, like which of the million actions did you do actually resulted in that reward you finally got? You know, which one do you ascribe the reward to? It's pretty difficult mathematically to figure those things out. And in a lot of cases, you just don't have any reward signals. So how do you drive your unsupervised learning? And it appears to be, certainly in humans and obviously children and even animals, this intrinsic motivation. Certain things they find intrinsically motivating. And there's quite a lot of knowledge about that in psychology and neuroscience. So for example, novelty seeking, encountering novel experiences is intrinsically rewarding for our brains. You know, it releases dopamine, and we learn faster in those situations. You know, the idea of knowledge gain, being information, being sort of rewarding in of itself. There's whole theories about that. You could even start thinking about emotions. You know, how are they evolved, and what are they for? And some of those things are, intrinsically motivating. And then if you build on top of that social structure, you get even more complex motivations for things that humans want to do in modern civilization. And in fact, sometimes those things can be gamed on top of our biological emotional systems and go awry. So we have to be careful of that. And then the other thing is in the social learning, and that's another huge area that I think is going to become very important in the next few years. Currently, we've mostly been studying AI systems that have been learning against an environment. But very soon, and in fact we're already working on this, we have a whole group that works on this, we have a multi-agent team that is working on situations where you have hundreds of AI systems interacting, maybe with humans as well, all in kind of like a community, and perhaps they're cooperating or competing or doing both, and what are the dynamics there? And I think that's going to be an extremely exciting area of research in the next few years. And in fact, I would say that's going to be the default, at least for us at DeepMind, is moving away from single agent environments to multi-agent. And then, I think that's going to be an incredible testbed actually also for the social sciences to actually experiment and see how multi-agent learning systems interact in group settings, which is quite difficult to do in normal experimentation.
Anything that?
Yeah, I mean, I think one of the difficulties is we have a pretty good set of tools when we have very crisply defined reward functions in sort of machine learning environments, but that's not the world as it exists. You have all kinds of very messy reward signals. You'd like to be able to specify rewards and goals as sort of abstract language that a system can then understand and incorporate into some sort of multifaceted reward function, and motivations and things like that all play into this. And I think that's really where the next many years of work will be. How do we actually build systems that can get a lot of the same properties that early learning seems to possess in terms of seeking out new and interesting creative ways to explore things and build on that.
So coming to language, we've obviously seen in the last even couple years amazing kind of acceleration for what kinds of language result we're seeing from the current research program. It's kind of the question of, some people think the Turing test in its first version, not the child version, the first sentence, not the second sentence, was actually already passed even by, early programs like ELIZA, in a specific context. Yes, there are very few people, but it's kind of like, can you fool one human being? Does that work enough? What do you think about kind of like all of this, the comprehension that's accelerating through, Siri, Google Assistant, Cortana, Alexa, and do you think that the Turing test will still be a good approximate for understanding, or what's the things we should add in as the approximates for understanding? And either of you can go first.
Okay, so so we've made some amazing progress in human language technology, and so speech recognition now, turning speech signals into words is really, really good, right? Any of you can pull out your mobile phones and you get amazing speech recognition on it. And recent work in deep learning at Demis's group has also led to huge advances in turning text back into speech. Both of those external parts work amazingly well now. But when we get to core natural language understanding of actually understanding the meanings of the words that people say, we're still very far from that actually working well. And so that's why half the time if you use Siri and you try and ask something, it says, "I'm sorry, would you like me to web search that for you?" because it doesn't actually understand what's going on. And that challenge is what Turing had in mind when he proposed the most famous version of his Turing test of someone talking to a hidden person or computer, and whether the person could work out it was a human or a computer. But I actually think that original Turing test has been shown to be misguided and not an effective test of intelligence. So Alan Turing was obviously a completely brilliant man, ahead of his times and things like that. But if you've seen the movie, you might have got a sense that his social skills were not his strong point. And an enormous part of human intelligence is actually social intelligence. And part of social intelligence is that we know how to interact in ways that people like. Little kids, very early on, when they're only a few years old, start to learn how to attract their parents' attention successfully and things like that. But going on, we're used to having social interactions with smart colleagues. And so we have this bias to impute intelligence when words come out, even if you're really playing a parlor trick where you're just saying halfway appealing dialogue. And so what people have been able to show very successfully is you can write systems for the Turing test where you're doing parlor game dialogue of just saying cocktail party, interesting things, and the human interlocutor will think there is intelligence there even when there is no intelligence. In fact, it even goes the other way. So there have been simulations of the Turing test, and one of the few human beings who has failed the Turing test as the other human who's being tested as to whether they're a machine or not was a person who was an English professor, and the human that was testing concluded, oh, no human being could possibly know that much about Shakespeare. That must be a computer, right? So there are a lot of issues with the original Turing test.
Well, I think one thing is that if you wanted to have a real version of the Turing test, part of the trouble is that human language depends on meaning, and it depends on being able to have this interface to the kind of abstract knowledge that Demis was talking about. So in order to have understanding, you sort of first have to solve the problem of having these abstract hierarchical representations of the world around you that are linked into just the sounds that we make. And I think it's worth pointing out that even if you think about our current language understanding, in some ways, it's a kind of multi-agent problem of the sort that Demis was talking about, because it very much depends on the fact that we have an internet full of really good language users. And to some extent, I always think this is a little like the Matrix, right? I mean, essentially what's happening is we're all being slaves to the natural language processing systems that are going out and asking all of these people, what's the right translation for this? What's the right translation for this sentence? So it's really sort of crowdsourcing that capacity that we have to connect our high-level knowledge to language, rather than just being able to do it from scratch. It's because we have all these other people out there who have those capacities that we can make those generalizations. But there was something else that I wanted to say, which is that I think there's an important point about childhood, which is more than just children can learn, but there's something about childhood itself that's special. So there was some mention about the evolution of human intelligence, and one of the interesting correlations is that large brains and intelligence seem to go with this extended childhood. And there might be something about the very fact that we have this protected period to do things like explore, and both internally and externally, that enables us to be able to develop these capacities later on. And again, in the case of language, we know that the capacity to learn certain kinds of aspects of language is much stronger in infancy, for instance, than it is in adulthood. And I think that's going to turn out to be true for some other characteristics as well. So it may not just be we want to look at babies because they're the youngest humans we know about, but there may be something really special about this design of having kind of a protected explore space on the one hand, and then an efficient exploit space on the other that is part of what makes humans as good as they are at solving those problems. And at the moment, if you look at even neural networks, they typically sort of have this unilinear development where they get more and more data and make more and more connections. And if you actually look at the human brain, what you see is there's this early period of both cognitive and neural exploration, proliferation, and then there's a period where you sort of switch from that very plastic system to a much more efficient and effective one at the cost of being able to do something like learn a new sound system, for instance. Mm-hmm.
Yep.
Just to follow up on a couple of those points in the Turing test, Turing is one of my all-time scientific heroes, but I don't believe that he meant the Turing test to be a sort of rigorous test in the way some people have taken it. I think it was more like a thought experiment. For example, he didn't specify the expertise level of the judges and so on, which I think he would have done if he meant it like that. I think the deeper part of the Turing test is really, at the time, I mean, obviously Turing was working with very primitive computers, or not even computers, sort of pens and paper. And he was just, that was the main mode of interaction, is through a terminal and some strings of letters. I mean, he couldn't have imagined VR and computer simulations and all the things we have now. So I think really what he would have meant was, well, the deeper sort of philosophical part of that is, what if we can mimic all the aspects of all the capabilities of a human to the satisfaction of another human observing it? Then what would that mean about that system? Which then I think it becomes a very interesting philosophical point that people like Searle and Chalmers and Chinese room theory and all these kinds of Chinese room problem, all these sorts of interesting philosophical problems have addressed is, does it really have understanding, even if it's exhibiting all of the right characteristics? Is it processing things in the same way? Is it conscious, etc.? That we would assume other humans doing those things would be. And I think he was just talking about text, this kind of rather primitive sort of dialogue, because that was what he could imagine at the time. And then just on the other point about learning, I think that one of the reasons we like reinforcement learning and as a paradigm is that, just like with children, we think that to learn things about the world properly, you need to be an active learner, right? So you can't. A lot of AI these days is passive learning. You get given a bunch of examples, you try and classify them or something. You're not really a participant in your own learning. And of course, children are, and animals are, and reinforcement learning agents are as well. Like what they know guides what they should do, and that gives them, and that determines what new experiences they're going to get. And I think that's very important. There's lots of theories in neuroscience. Lots of neuroscientists propose that action is required for perception. Even you can't really properly perceive your world without action. So there's a whole area of neuroscience called action in perception that advocates this, that you really need to be able to act in the world to properly understand your perception. And I think that's very interesting. So I think that this active learning part is a key thing that we have, that we take from animals and natural learning, that they're active learners.
So this will be the last question maybe before we go to questions from the audience. There will be 4 different students with microphones in different areas. So if you're thinking about a question you're going to ask, you'll raise your hand. The student will come to you. You'll have a mic. You'll know that it's your turn to ask a question because I'll see you with a mic and you'll stand up. So for the last kind of part of this technical thing, how does the fact that we can look under the hood with AI change this kind of concept of does it have understanding, right? Because we obviously do various forms of looking under the hood with humans in terms of MRIs and study of the neuroscience and all the rest, but there's limits to how we can do that for kind of obvious reasons. How much does the notion that we can actually, in fact, go and do introspection, even in these very complicated neural nets, change our view about what the research path looks like?
I mean, I think one of the real advantages of computing systems is that they're very instrumentable, right? You can instrument anything you want. And that really can help us inform, what experiments do we want to do in order to understand some hypothesis we might have about how the system is behaving. It can actually also inform how we think about designing experiments that we then might want to replicate in real intelligent systems, intelligent organisms, to then understand, does that property seem to actually occur in real systems as well. So I think that interplay is really important, and the fact that computing systems have this malleability and measurability at any sort of arbitrary level that we don't currently have for real organisms really does help.
I'd agree with that. I mean, I think we're at a nascent stage of understanding these systems. I mean, I think the way I explain it is we're kind of in a transitory period where we've only just recently got these systems working, in a sense, to do anything impressive in the last sort of 5-10 years. And then the history of and AI is an engineering science, right? The history of that is that you build something, you get it working, it does something useful or impressive, and then you can start reverse engineering it and doing ablation studies and all sorts of things that are obviously much easier with virtual neural networks than you can with the real brain. And we have a research program at DeepMind called Virtual Brain Analytics. And what I always say, and we have a very big neuroscience group led by this brilliant neuroscientist called Matt Botvinnik. And what I always say to that team is that we're in a situation at the moment where we understand, we have less good tools for understanding these virtual systems than we have for the real brain. We don't have fMRI or equivalent of those kinds of things, but we should do. And in theory, in the next 5+ years, we should be in an even better state because of the fact that these are virtual systems. So you can record, if you want, from every single single neuron in the brain. We can completely control the stimulus input in ways that you can't even with very controlled animal studies. And so, if anything, we should eventually be in a much better position of understanding these systems than we are even currently with the brain, the human brain. And I think that's what's very exciting, actually, about this AI approach of using sort of neuroscience-inspired AI as an approach to building AI. Because I think eventually, when we start distilling intelligence into this algorithmic construct, if we compare that then to the human mind, I think that would be one of the best ways to make progress in understanding what's unique about our own minds. Things like consciousness, creativity, dreaming, all these debates that we're sort of in the philosophical realm at the moment, we can probably bring them into the empirical sciences by comparing the capabilities of the human brain with these sort of artificially intelligent systems and seeing what's missing, what's if there is something missing, what it is, and then kind of try and decompose that in something and hypothesis test what that might be.
I don't think I have anything very different to say, so I'll keep it short, but I'm a huge believer in constructive models of understanding. That the fact of the matter is, whatever your analogy is, sort of understanding flight, we just didn't have a very good model of how flight works when it was just, okay, birds flap their wings and fly. It's once we started trying to construct airplanes that we understood a lot more about aerodynamics, and I think it's exactly the same with human brains, that until we started trying to construct machines that could think, we just had no idea of the complexity that was in our heads.
Yeah, I mean, I think the idea, we know that there's computational systems that can do all the things that children can do because we've created them. And actually, it's much easier and more fun to create them than it typically is to create computers. They're children. I mean, we know that they're or at least our very best bet is that there's some kind of computational system built onto a brain. And I think for a long time, the point of cognitive science has been to try to say, can we use that, can we go back and forth between understanding how those computations are possible? That's the best way we know of actually understanding what our brains are doing. And vice versa, going back and forth and saying, if we understood that, then that would be the way to create new systems. So that's been the point of cognitive science for a long time. And I think it's starting to be very productive in the light of the new developments that we've had in AI.
One of my own personal hopes in this kind of introspection question is that there's this classic philosophical conundrum of when is it correlation, when is it causation, and what are our models of causality? And maybe as we begin to be able to look a little bit under the hood, we begin to get some ideas both on when we actually have a model of causality versus correlation, and then maybe that will even share something on philosophy. But it is now time for audience questions. So, does someone have a mic yet?
Good morning. I have a question about pedagogy. My passion is teaching deep learning and neural networks to the marginalized, people who don't have a background in linear algebra, multivariate calculus. And my question to you is, do you know of someone who is putting together a curriculum that people starting from no background can use to march up to the point where they can have a conversation with the generals in the army? I know that Andrew Ng talks about building that army of 1 million engineers to implement this dream that I think we all share here. And when it comes to pedagogy for the 90% of the people without the background, do you see it as we need to create that? Or do you see it more as, hey, we're on the verge of having libraries for all of this, and therefore the marginalized won't have to know how to do linear algebra or calculus? Thanks.
I mean, I think one of the great aspects of the modern internet is that there's lots and lots of different kinds of material available to teach concepts at all kinds of different levels. And so, our group, for example, has a thing called TensorFlow Playground, which is designed for people who don't have a background in linear algebra. It's really a visual system for exploring how very simple neural networks learn. You can get a lot of benefit from just interactively playing with this. Let's try creating a neural network with 2 neurons, and does it learn to distinguish red and blue in different areas of some space? And that actually can interactively teach people a lot about the intuitive concepts without necessarily getting into the sort of deeper mathematics behind these kinds of systems. And I think one of the real benefits is that there's material available at lots of different levels for people, and there's then an on-ramp for, like, you don't have linear algebra, here's an earlier thing you might want to do, and even an earlier thing you want to do, and eventually, and you can take that in many different ways. Like if you care about being able to use machine learning without necessarily understanding the theoretical basis, but want to then make it do something practical for your problem or your creative endeavor, you can do that without necessarily getting a PhD in machine learning. And I think that's really one of the benefits of this sort of the fact that we can use these techniques in so many ways in the world that not everyone needs to be a PhD in machine learning, but we can have pedagogy that allows for that.
Yeah. I'd be careful what I say because he might watch the video of this later, but my 11th grader is doing a machine learning class in high school at the moment, and if I'm frank, he doesn't understand much about machine learning. But on the other hand, with the wonderful libraries and frameworks that are available now, I mean, I've just been gobsmacked by how much he's managed to be able to do. That, hey, I built a reinforcement learning agent, which he's got in his three-dimensional world, and he's actually gotten the thing to work. And I'm going, wow, how can someone who's not a graduate student be doing reinforcement learning now? So I think these modern libraries for machine learning have just had an amazing transformative impact. So to some extent, the bottom line of what you need now is, gee, you should practice up your Python programming, but that's essentially all you need.
Let's go to another question. Great. Hi, Eric.
Hi. So I enjoyed this discussion very much about the Turing test and also about using the human mind as a model for artificial intelligence. And as Demis mentioned, it's the only real existence proof we have, so it narrows the search space. It also gives us insight into how our own minds work. But there's another side to it, coming back to what Fei and John were saying in the beginning, that we want to build machines that complement, not substitute, for humans. And the more similar you make a machine to what a human is currently doing, the more likely it is to be a substitute. If you can make it augment and have very different capabilities, then it's more likely to create shared prosperity. So the question is there a way to get the best of both worlds, to learn from the human brain, but also build machines that primarily augment humans as opposed to replace them?
Yeah, I think it's a great question. And I think, when we talk about taking inspiration from human intelligence, I think, someone mentioned earlier, maybe it was Jeff, we're not trying to slavishly copy the mind. I don't think that's the right way to build AI, and it wouldn't be good for the reasons you're talking about. And I think there's no need, because silicon and carbon have different strengths and weaknesses, and we should try to build, and I certainly see AI as an amazingly powerful tool that could augment human endeavor in all sorts of areas. I'm personally excited about accelerating science in that way. And I think we don't have to worry too much about that in some sense, because the strength of silicon-based systems is very different. You can do things like Monte Carlo tree search and perfect memory, lots of things that humans don't do. And on the other hand, what we'd be debating on this panel is things like creativity, emotions, other things that we think of as very human-based, and social learning. So I think there's a lot of very big scope there for collaboration and cooperation to augment what we as humans are able to do.
Another question? Do we have? Great.
Thank you. I'd like to follow up on your point about silicon versus carbon. There is an architecture underlying all of modern computers known as the von Neumann architecture, which separates memory and processing. And it appears that the brain co-locates memory and processing with each individual neuron. So I'd like you to comment on what's going on today with TPUs and other AI-based chips, and where that might evolve in the broader neuromorphic computing system. And then finally, I'd be curious to know whether or not you believe these sorts of chip architecture changes are required to get to AGI, or if you believe we could get there without such changes.
Sure. I think over the last 5 or 8 years, we've seen tremendous advances in the kinds of mostly deep learning-based models that we want to run on a wide variety of problems. And the computations in those models are actually much more restrictive than the kinds of programs you want to run on a general purpose CPU. And that brings about an opportunity to create specialized machines that are good at those kinds of computations, but aren't good at completely general purpose computations. So if you want to do low precision dense linear algebra kinds of operations, which is the bulk of what these building blocks rely on, then you can now consider building specialized hardware for that. And because it's specialized, it doesn't need to do everything, and there you can get tremendous efficiencies in terms of power, in terms of computational ability per watt or per dollar. And that's why you're seeing these kinds of architectures happen, and there's now a giant experiment going on with lots and lots of startups trying like different ideas in this general idea of specialized hardware space for machine learning that's now playing out in the sort of the venture ecosystem. I think these are going to be really, really important tools because general purpose CPUs are not improving in performance, and we know that computation is one thing that improves generally the kinds of systems we're able to build. Like it just enables us to do more, to build more powerful models that are better at different tasks. So, and I think looking at neuromorphic kinds of things, things like spiking neural networks and so on, is pretty interesting because they have very low power characteristics, but I don't think we necessarily know how to use such systems. So we haven't sort of really gone in that direction in terms of the specialized hardware more recently.
Unless critical, I'd like to go to the next question. Okay, great.
Thank you for joining us today. This is Lamia Youssef from Stanford University. And I'm curious, Feifei earlier mentioned the pitfalls of machine learning and AI, and especially as we're talking about general intelligence. Where does the responsibility of regulating and basically the application of different machine learning applications in different areas falls on? Is it the engineers, is it the governments, or is it policies, or is it a collaboration between all of these?
I think the short answer will be all, but will someone start?
Yeah, I mean, I can say first, the field is moving very quickly, so I think that's an important thing to keep in mind when we're thinking about regulatory aspects. But I think you want regulators to be informed, so understanding where the field is, where it's going, is really important to help craft the right regulations. I think a lot of it depends on the application to which these systems are being put. So medical applications actually already have frameworks in the FDA and other regulating bodies for regulating medical devices. Some adaptation of those for machine learning systems is probably better than creating completely new kinds of regulatory frameworks. I think it's on all of us who are building these systems to come at the ethical issues with integrity and principles. And that's one of the reasons within Google last year we put out a set of principles by which we consider uses of machine learning and AI in our products, and also a set of things we will not do. I think that's been helpful for framing our own thinking, and also we made them public so that other people who are wrestling with these kinds of issues can think about it. But the issues of fairness and bias and equity really are important things to think about whenever you're thinking about a machine learning system, because they can perpetuate the world that we live in and the biases that exist in ways that accelerate them in some cases. And so I think, all the above is probably the right answer, but it's really important.
I think it's important to say, this is not a new problem for human beings. To some extent, the evolutionary design of human beings is that we have this capacity to generate new technologies, whether they're technologies like computers or even just technologies like new uses of language. And each generation has innovations and then has to deal with the unforeseen consequences of those innovations. That's just what being human is. And I think one of the things that's characteristic about humans, which is still not characteristic of AI, is that we can actually change our objective functions. So what we can do in AI is we can say, look, here's the objective function. We want you, this machine, to fulfill this. But what we can do is we can say, no, wait a minute. Maybe that's not really the goal that we want. Maybe there's another goal that would be better. Maybe that's not how we should decide who's guilty and innocent. Maybe we should do that a different way. And so far, at least, that's a really uniquely human capacity, that capacity over cultural time to change the things that we think are important. And that's going to continue to be something that human beings are going to do. But, since fire, at least, we've had this problem about when we innovate, which is our great advantage, we always have unintended consequences, and then we always have to come in and have a generation that figures out how to deal with those unintended consequences. So that's part of all of the above. But this is something that humans have always had to do, and that we're sort of kind of good at least for now.
So the timekeeper has given me the signal that it is time. I really appreciate the last question because to some degree, all of the above is part of why HI is created and launching today, because it's bringing industry, academia, government, public policymakers together in order to discuss these things. One quick logistics thing, which is lunch is next. In anticipation of lines getting back in, please try to come back a little early. Don't wait until the very last moment, because otherwise it'll be slow. And obviously, because after lunch, Bill Gates will be kicking it off. And so with this, please thank our amazing panelists.